Hello friends, this video on chemical bonding part 20 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 19.
So there are different types of overlapping in the nature of covalent bond, and there are generally two types of overlapping or bond, I can say. One is the sigma bond. In sigma bond we have SS overlap and SP overlap and PP overlap also. For pi bond we have only PP overlap. We'll see all this sigma bond and pi bond. Just understand that we have two types of bond, sigma bond and pi bond. Sigma bond can happen in three different overlap case and pi bond can happen in one overlap case. So please note that this is all covalent bond. These are not ionic bonds, all covalent bond. Right? Let's discuss the sigma bond. Sigma bond is formed by end-to-end or hand-on overlap. It's a head-to-head overlap. Head-to-head overlap of orbitals along internuclear axis. Please note, head-to-head overlap along internuclear axis. Correct? And the sigma bond allows free rotation and cylindrically symmetrical about internuclear axis. We'll explain this. The sigma bond, as I told, of three types: SS overlap. So if I have SS orbital and head-on, if they overlap, they becomes SS overlap. SP, if I have S orbital and I have P orbital, if they overlap head-on, they become SP orbital. And you will see in this case also, if you see, this is my internuclear axis. So if you see, this is cylindrically symmetric about this internuclear axis. You take any point, it will all be symmetric. Right? Because it will be three-dimensional. Maybe once we'll take the three-dimensional shapes, or when we have three-dimensional animations with that, it will be pretty clear to you. For PP or overlapping also, if you see, there's a p orbital, it overlapped like this. There's a head-on overlap actually, and if you see, this is cylindrically symmetric, and it allows free rotation because this can rotate. I think we can take an example where we can show it allows free rotation on the motion. So let's take this free rotation thing. This is the three-dimensional of p orbital. See, p orbital overlapped with p orbital. Now if you see, this is my internuclear axis and everything is symmetric along this axis. So if you see, you take these points, any of these points, this will all be symmetric. And this is the overlap. This is a p orbital. This is a p orbital head-on overlap. Right? So if you see, for example, my methane, the formation will explain later. Just understand this how methane is forming. So I have this PP overlap. This is my PP overlap, and then this hydrogen is attached to this. This is the actual shape of methane we have. So if you take this orbital here like this, so everything is symmetrical about this orbital, and these guys, these can rotate actually. So we can rotate, you can flip this. For example, if you see this methane, you can rotate this. It won't break, it can rotate because this has become one axis now, and these three can rotate. It can rotate like this. This is my methane actually, C2H6. That's the actual structure of methane as proposed by valence bond theory. We'll explain more in this when we explain the different kind of hybridization. Just understand this, the methane looks like, and you can actually rotate this whole methane can, this particle, right, this thing can rotate, and this is my internuclear axis. This is a p orbital, and it can rotate. Now we'll discuss pi bond. So in pi bond, the overlap is such way that axis remains parallel to each other. Right? And these axes are perpendicular to internuclear axis. We'll show you an example. So if you see here, there are two p orbitals, and the way they are combining is not head-on. This is like this. They are combining like this. Right? There's an overlap, and their axes are parallel anyway. If you see one more example, in this case also, right? Their axes are always parallel. They are parallel to each other, right? and this is the way it overlaps. And if you see the way it overlaps, it forms a saucer-like cloud. This is saucer-like cloud it forms. It forms saucer-like cloud. If it overlaps like this, it forms saucer-like cloud. So if you see it's sideways overlapping. So in earlier case we had this two orbitals, it overlapped head to head, right? So in this case we have two orbitals and it overlaps side to side. This is pi bond. It's weaker bond actually because the overlap extent is little less, and this is my sigma bond, this is pi bond. This is denoted by this symbol sigma and this is by a symbol pi. So in pi bond there is no free rotation. We'll take one example. So if you see in this case, this is my ethene C2H4. So if you see here, this was my sigma bond head to head, and this is my pi bond. So if you see, this will form a bond like this. This will be one bond, right? This will be a cloud like this. If you see, this forms a cloud like this, correct? It's a cloud like this. So if it is a cloud like this, it will restrict the rotation. It won't be able to rotate. You can't rotate this because see, if it is like this, if you have something like this, right, you can rotate it. But if you have something like this, where you're merging these, right, you can't rotate because there's two bond. There is only single bond, sigma bond, so it allows free rotation. But the moment you talk about this pi bond, because this is a pi bond now, right? We talk about pi bond, it forms a cloud like this, saucer kind of cloud like this, and this will restrict the free rotation. Correct? See, this is my sigma bond and this is my pi bond. This is one pi bond actually. So it looks like from the figure it's two, but this is one pi bond. This is one pi bond actually. So if you see the structure, it will be like this. So in this case, this is the first is my sigma bond and the second is my pi bond. This is my sigma bond, one bond, and this is my pi bond. And actually if you see, all these bonds are my sigma bond, because this is a sp overlap, sp overlap, sp overlap, sp overlap, right? There is a p orbital, p orbital. This is all sp overlap. This is all s. These are all my sigma bonds. These are all sigma bond, and this is my pi bond. And this doesn't allow free rotation. This is my shape. So let us discuss the strength of sigma and pi bond. As I told, the strength of the bond depends on the overlapping extent. So in case of sigma bond, the overlapping is more large extent. So the sigma bond is stronger. Sigma bond is stronger than pi bond, right? And we always know that pi bond is formed in addition to sigma bond. The first bond will always be sigma bond. For example, in case of ethene also, the first bond that got formed was sigma bond, and then only we got this pi bond, right? If you have a pi bond somewhere, sigma bond has to be there, because the first bond that is formed is sigma bond. In addition to that, we get pi bonds, right? And pi bond is always present in the molecule which has double or triple bond. For single bond, it's always sigma bond, single bond. For double or triple bond, we have pi bond. Please note, sigma bond, single bond. For double and triple bonds, we have pi bonds. So let's compare sigma bond and pi bond. So this is my all sigma bond on the left side. So sigma bond is formed by the overlap of orbitals along the internuclear axis. If you see, this is my internuclear axis. So overlap happens along this line. So I get this type of bonds, right? And this is formed by sideways overlap. This is my two internuclear axes. They are always parallel to each other. This is sideways overlap. This is formed by SS, SP and SP overlap. You see SS, SP and SPP overlap. So this is PP overlap. And this is formed only by PP overlap. This is strong, this is weak. In this case, the electron cloud is symmetrical about the line joining two nucleus. This electron cloud is cylindrically symmetrical actually. Cylindrically symmetrical. And this electron cloud is not symmetrical. If you see this, the electron cloud is not symmetrical about this this line. If you see, right, this place is not symmetrical, right? Somewhere you get something else, here you get something else, here you get something else. If your case, in this case here you see, you go any direction, you get the same electron cloud. So this has one electron cloud. If you see in all the case one electron cloud, this has two electron cloud, one up, one down. In this case the free rotation is possible, in this case the free rotation is not possible. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.